we have Ted Southern from Final Frontier Design. So he's been working with NASA to design the next generation of spacesuit gloves. He's a sculptor, costume maker, and inventor from Brooklyn. And for the last 4 years, he's been developing a new generation of spacesuit gloves in coordination with Nikolay Moiseev, a Russian spacesuit fabricator. In November 2009, Ted and Nick outperformed NASA's current Phase 6 spacesuit gloves and won second place in NASA's Astronaut Glove Challenge. Prior to space, Ted's work focused on technical garments for movies, theater, and television, including wings for Victoria's Secret angels and costumes for Cirque du Soleil. So he's going to speak to the Empiricist League about designing garments for outer space. So please welcome Ted Southern.
Thanks. Wow, this is going to be a tough act to follow. I'm not sure I can talk that quickly. I'm going to be a little bit slower in my enunciation. And also, my introduction just gave away half my talk, but that's fine. We're here to talk about future histories, right? And so I kind of wanted to talk about my predictions of the future of what we'll be wearing. I believe that humankind is destined for outer space. And right now we use spacesuits that are designed maybe 40 or 50 years ago. And I think there's room for a whole revolution in technology in space, but we're still getting there. So it all started with me with the NASA Astronaut Glove competition in 2007. You can kind of snicker at the idea of glove technology, like why would that be a thing? But NASA's actually really concerned about this. So astronauts are essentially plumbers right now on the International Space Station. There's a lot of quick disconnects and plugs that they have to plug in. And in microgravity, they actually walk with their hands. They translate with their hands. We, as humans, use our hands to interface with the world. And I'm deeply interested in hand functionality. And I always point to this example that you could argue that our ability to perfectly oppose our thumb to our fingers drove our cerebral cortex to language, because we needed ways to talk about the objects that we're manipulating so well with our hands. So that and a combination of a series of injuries that I suffered made me very interested in this when I was in graduate school. So I went to Pratt for sculpture about 10 years ago. And while I was there, everything I did had to do with hands. I built in detail all the ligaments of the hand connected to different parts of the bones, and really tried to understand what it was that was malfunctioning in my own anatomy. But also, my goal was really to help extend the ability of the human body, to help us do more. And that's been my goal for a long time. And so when I read about NASA's astronaut glove competition, it really fit a lot of the questions that I was working on anyway. The competition itself was a citizen inventor challenge, similar to the reason Charles Lindbergh flew over the Atlantic, or why the watch was developed hundreds of years ago. The government put up some money and said, if you can do better than this, we'll give you some money, because we're not getting good ideas out of industry right now. This is a picture of the 4 gloves that were in the glove competition. This is NASA's glove here. This is my now partner Nikolay's glove. This is my glove here, and this was the winner of the 2007 glove competition, Peter Homer. So I didn't win. I entered it as an artist, as a conceit to build some work for graduate school. But I learned a lot, and I met this guy here, this square Russian man who got an aerospace engineering degree in the Soviet Union in 1986, started working for Zvezda, the Russian spacesuit company, in 1988. His gloves flew on Mir and on Mir shuttle missions, and also ended up leaving Zvezda after almost 20 years working there as the lead spacesuit engineer. He'd worked with NASA and the European Space Agency. And you see him here in NASA's EMU, Extravehicular Mobility Unit, and also in the Mars Yard in Houston. So Nick and I met at that 2007 glove competition. We both lost. We were both pretty sad about that. It was $200,000 that just went away because we didn't win the competition, and he needed to ride back to New York, and so we made friends. Very, very different person than me, but we ended up deciding to partner together. NASA had a second glove competition. Long story. It has to do with the pressure garment versus the outer garment, et cetera, et cetera. Here's some pictures of the second glove competition. You can see a guy from our competition, ILC Dover here, measuring the torque of the adduction of the glove while it's pressurized. So long story short, we ended up outperforming NASA's current glove technology under pressure. We won $100,000 from NASA and started a company that way. And that was awesome. We got to meet the administrator of NASA, Charlie Bolden, and go down to DC. We went to Houston. We ended up contracting with NASA. They invited us to Houston, and they said, you should do this. And I thought, okay, well, I'm going to do this, which is a terrible idea. If NASA ever tells you to do anything, don't do it, because it's I'm really proud of the work that we've done, but Spacesuit Company I've pretty much identified the smallest possible market of anything in the planet. But we've worked really hard at it. So this was our second full suit in 2011, 2012. There's two kinds of spacesuits. There's one that's used for launch and reentry, and you wear that inside a vehicle in case of loss of cabin pressure. And that's a lot like the oxygen mask that falls from above in case of loss of cabin pressure in a commercial airliner. But this is for, orbital altitudes rather than 35,000 feet. So this here is an IVA suit, intravehicular activity, or launch and reentry suit. And we've built 8 of these. We're now, at this point, we're at TRL 6, which is one before flight technical readiness level, not total request live. So we've built a lot of suits over the years, and I'm really proud of that. We've done some pretty interesting testing. This is a pressurized flight in a glider. Gliders are really interesting applications for spacesuits because they have all the same drivers as rockets. You have to fit in a small space. It has to be lightweight. It has to be, all the standards that you want the suit to be comfortable and functional. But there's no rocket, which is pretty convenient. And we've incorporated a lot of technology. We started out milling a lot of our parts, and now we're 3D printing. So this helmet ring is entirely 3D printed, as opposed to 7 years ago when we started, that wasn't really an option. So it's pretty exciting to watch technologies unfold. And I really do believe that the reason we're able to do this, to compete against literally the military-industrial complex, is because computing power and access to technology has become democratized, and I think that really is the driver behind what I'm seeing now as the new space revolution. At the same time, we've continued to work on gloves. Most of our funding has actually come from NASA for components of extravehicular spacesuits. So I explained the one kind of spacesuit, the launch and reentry suit, that's like the oxygen mask. The other suit, the one that we're more familiar with probably, is the EVA spacesuit, extravehicular activity or spacewalking. And that's where you leave the vehicle willfully, you decide to go outside, you're either in microgravity or you're on some planet, and that's a whole different story, right? There's a lot more emphasis on mobility and functionality. You're nominally pressurized. In an IVA suit, if everything goes right, you don't have to pressurize that suit. Your cabin has pressure and you're fine. But once you leave the vehicle, man, things are problematic. Space is not a forgiving place. We are creatures of the Earth, and there's a lot of problems in space. The biggest one, I believe, that the spacesuit is trying to solve is the pressure garment. And that's really why I'm here. I'm not here to talk about myself or my background. I'm here to talk about what I believe is the future of spacesuits. So this is the standard right now. This is gloves that we delivered to NASA in 2015 for an SBIR, specifically designed for Mars. So they're higher operating pressures than the ones used today to reduce pre-breathing and risk of decompression sickness. But this is just one layer in what is maybe a dozen layers of the spacesuit. So there are layers inside and outside of this. But this is the most important layer, in my opinion. The pressure garment is where all the load happens. There's a lot of gas force and pressure differential inside, and so that's really what's restricting the garment. It's like a big balloon. It's like a big human-shaped balloon, and that's pretty much been the history of spacesuits since the beginning, since Yuri Gagarin and John Glenn and the NASA astronauts, Alan Shepard. Over that pressure garment goes what they call a TMG or EPG, thermal micrometeoroid garment, or environmental protection garment. NASA is full of acronyms, don't even get me started. This one is particularly designed for the Martian environment. We've done other stuff. I won't talk about that now. What I'm here to talk about is the future, right? So this is today, and this is a rather exaggerated version of what astronauts use today, but it's pretty accurate. A big bubble. This happens to be an all-hard suit, so it's all fiberglass, and all of these lines that you see are bearings that are canted to allow for motion, but it's a really strange motion where in order to reach here, you kind of have to move around in order to get the bearings to work. Big bubbles, big balloons are problematic, and I don't think that's how things are going to work out in the future. I don't think we're going to go to Mars effectively. I don't think we're going to explore outer space with big bubbles around our body. We do need gas around our head, for sure. Like don't go expose yourself to a vacuum without gas around your head. You can't get around that. But conceivably, the rest of your body doesn't need the actual gas. You need the pressure that the gas imparts against your body. So right now we're at about sea level, and there's maybe 80 or 90,000 feet of atmosphere above us pushing down on us. At sea level we have about 15 pounds per square inch of air pressing in every direction, and pressure from a physics standpoint is even and normal. So it's perpendicular to every surface and perfectly even. And that is a beautiful thing. If you don't have even pressure on your body, your blood is going to start pooling in areas where there's lower pressure, and that's a big problem. So with that in mind, there is an idea of this thing called a mechanical counterpressure spacesuit. It's not a big gas bubble. There is a bubble around the head and a seal around the neck, which can be very uncomfortable. But the rest of the body is just compressed. And the idea is to use the garment itself to compress and to mimic that gas pressure that we're getting freely and normally otherwise, even to the amount of pressure that you have in the helmet. Sounds like a great idea, but in practice, it's really difficult to get garments to push against your body evenly and normally. If your body was one big sphere and didn't move at all, that'd be great. And maybe that's where we're headed, Maybe William Burroughs was right, and we're all just tadpoles destined to change and reform. But for now, we have hands and arms and legs and really annoying things like armpits and genitals and backs of the knees that can't be compressed very evenly and normally. This, by the way, is the biosuit developed by MIT. Really interesting concept suit. They've mapped out things called lines of non-extension on the body, where no matter how you move, these lines wouldn't get longer or shorter. And the idea is that those lines would contract as the pressure changes, and the suit would just shrink around you and replace the gas that's around your body. In reality, these are motocross gloves and motocross boots, and there's a lot of folds in the armpits and backs of the elbows, and it's just a costume. They have done some testing, and it's not to diss the MIT biosuit, but it does drive me insane because it's in the AMNH, it's in the Smithsonian. This month we were in Aerospace Magazine, and it was like the lead picture in Aerospace Magazine, and it's a costume. And that was my old life. That's what I used to do. So this idea of mechanical counterpressure has been around for a long time. There's a lot of talk about Kim Stanley Robinson just recently, Red Mars, Blue Mars. And I was really excited to read that book and read about mechanical counterpressure in that book. And that's what I'm working on now. So it was pretty exciting to read sci-fi and be like, wow, that's my current NASA contract. This is a NASA rendering from the 60s from Honeywell. It's a Honeywell rendering of a NASA mechanical counterpressure suit on Mars. This is a concept life support system that MIT put together that I also don't believe in. But you see this concept of mechanical counterpressure throughout sci-fi. And that's kind of what I'm getting at here. Is I really do believe this is the future, and I believe that it's part of my mission and my ideal to create this. We saw it in The Martian. This is a mechanical counterpressure concept suit. You can see it's intended to be tight-fitting. It's not very tight-fitting at all, but it's intended to be. But the exciting thing here is this actually happened. In the 70s, this guy, Paul Webb, wore something he called the space activity suit in a vacuum chamber for maybe 30 minutes, not very long, but he proved it. He proved that it could actually work. It wasn't very elegant. He kind of had a fishbowl on his head, and it was 8 layers of elastic on his body. So I'm thinking kind of like a 9mm wetsuit that's 4 sizes too small for you. So you just sort of, like anatomical position. But he was able to move in it. He was able to function in this mechanical counterpressure thing. This was NASA-funded testing in the 70s. So this is 40 years ago, 45 years ago. And I am disappointed that there hasn't been more research and funding in this concept, but NASA is risk-averse, and there are a lot of problems in practice with mechanical counterpressure. It's really hard to put the thing on because it's so tight. You compare this to like medical level compression garments. You need a prescription for anything higher than 30 millimeters of mercury compression on your body. And normal, you can buy medical compression garments from Jobst that go up to about 50 millimeters of mercury. A good mechanical counterpressure suit would be more like 250 millimeters of mercury. So it's really, really tight. And we, as a company, Final Frontier Design, kind of sat down and decided, like, we think this is the future, so we need to concentrate on this. Like, we've done all these pressure garments, and it's awesome, and like we're proud of the work, but we think that mechanical counterpressure is the future. And I'm happy to say we got a contract with NASA in 2015 to design, test, validate, build, deliver to NASA mechanical counterpressure gloves. And that's what these are here. So around the forearm, you have a seal. The idea is we're testing this in a vacuum chamber glove box. So there's a seal around your wrist, and the gloves themselves compress around the hand to mimic that 250 millimeters of mercury. This is basically the concept around this. There's an inflatable pocket that runs on the backside of the finger, represented here by this air chamber. After you don the glove, that pocket inflates and pulls the seam allowance closer as it inflates in this direction, and basically just tightens around the hand. It's not 8 layers. We were really proud of that. It does rely on air pressure, which is a conceit. It's something that we can do today. That MIT biosuit that I was talking about relies on concepts of shape-changing fibers that don't exist today. And really the whole point of this was to deliver something today that would work now. We did a lot of testing this. One of the biggest challenges was validating it. How do you prove the amount of pressure that you're getting against the body with a really tight-fitting garment in a really mobile, dexterous area? So we built a whole series of sensor gloves that had all kinds of little FSRs, force-sensitive resistors, all over the hand. It was a real challenge to validate the measurements that we're getting out of those things and to prove to NASA that we're getting good compression. There's some pictures of the testing that we actually did. This is Richard Rhodes from NASA JSC Cruise Systems in our vacuum chamber glove box with the mechanical counterpressure gloves. And this is the readout that we got from that prior sensor glove system. It's just a screenshot of the compression we're going for. So this was the ideal, between 4 and 4.5 psi. This was as we're pressuring up. You can see in a variety of places where we were at. Doesn't look that great in that picture, but we actually were underwhelmingly approved by NASA as having things that are adequate. It sounds like not much, but it's actually a huge deal to have gloves that can function in a completely different pressure than the one that we're operating in. So the arms outside of here are in normal ambient pressure. Inside the chamber, they're at almost 5 psi differential lower. And without that glove protection, your hand would expand and blow up. You wouldn't actually blow up, but all the blood would pool in your hands. You're like a water balloon, essentially. We're all just water balloons. You can kind of see some of that here. This is after about 45 minutes of testing. The right hand had that sensor glove, and around the wrist there's a lot of wires, but you can definitely see where the mechanical counterpressure started, where the seal was here, and the difference between before and after. A lot of broken capillaries, but essentially hands that are intact. Thanks for that vote of confidence. I firmly believe this is the future. This is where we're going to head with spacesuits, and I want to see more of this. So after the contract, we pushed the idea and built a full arm that I very bravely tested in our vacuum chamber glove box to about a 2 psi differential. This arm, the full arm, weighs about 11 ounces, and NASA's current pressurized arm weighs about 22 pounds. And if you consider price per pound to orbit on shuttle was about $20,000 per pound. And current NASA spacesuits like the Z2 suit weigh about 250 pounds. It's pretty hard to ignore the advantages of this kind of system. There's no bearings necessary. A normal spacesuit would have bearing at the wrist, at the forearm, and at the shoulder. Bearings foul pretty easily in dust, and there's a lot of dust on the moon and Mars. So I'm pretty excited about mechanical counterpressure. We have a concept now to move from just the arm to a full suit. Pretty much any mechanical counterpressure suit is going to have to be a hybrid because you have to have gas around your head. But there's a lot of problems with your torso. You're breathing in and out, and so your chest expands and contracts. And counteracting that in mechanical counterpressure is challenging. I mentioned earlier your genitals. That's a big problem to compress things evenly and well. So our concept now is to have seals around the shoulders and around the hips, just below the crotch. And essentially a pressurized torso. Oh, I'm done. Pressurized torso, mechanical counterpressure arms and legs. And that's it. Good timing.
Why wouldn't you just design a suit that was filled with some type of liquid?
Sure, yeah. So we're working with this artist, Sarah Jane Pell, who proposed an idea like that for Mars. There was a suit that's filled with water, essentially, that could be pressurized as well. You have the same issue as a bubble in a pressurized liquid suit. There's a differential. Even though the liquid doesn't compress, it has to be pressurized to a certain extent. And so the joints in a compressed garment, like a balloon garment, have some restriction and would have to be offset from the body, so you have added bulk. So there's some advantages to it, but the mass and bulk of it are essentially the same as a pressurized gas bubble. Liquid behaves like a gas.
The questions are around using sensors. Do you think the price of sensors is possible? Because it has to adjust. And how do you deal with energy and computers that might have to deal with those sensors?
Certainly the access to technology and price of sensors has enabled us to make things like that sensor glove. Sorry.
How do you deal with computers and energy? Because these might be more energy intensive.
Sure. So we're trying to validate a system in this sense. In the actual, if you're going out to Mars to wear the mechanical counterpressure suit, you wouldn't have a bunch of sensors measuring the pressure of the suit. You would have already validated that, so you wouldn't need to actually bring it with you, fortunately. It's a huge problem putting electronics inside of spacesuits right now because it's pure oxygen inside, and so electronics are really problematic because human flesh is flammable in pure oxygen.
Okay, last question.
You mentioned how often the astronaut uses their hands. With the mechanical counterpressure, is there a loss of like dexterity or?
So that's the big advantage, is there's an increase in dexterity. It's remarkable how much astronauts lose in a pressurized glove. They have about 30% range of motion compared to no glove with a glove. And the grip strength falls about 60%. So we have measurements of like, how much with a hand dynamometer can you squeeze before and after. In the testing with our gloves, the range of motion was more like 70% of nude range, and the grip strength loss was about 35%. So there's some big advantages around mobility and things like using your intrinsic muscles of your hand to add abduct versus just flexion extension, which is really only possible with pressurized gloves. So,
Thank you.
thank you very much.